Lesson 1.4 Understanding LoRA and QLoRA Learning Objectives. By the end of this lesson, you'll be able to explain why full fine-tuning is out of reach for most developers, understand exactly how LoRA works under the hood, calculate memory requirements before you ever touch a GPU, and make an informed choice between LoRA and QLoRA for your own projects. These aren't just theoretical concepts. Every one of them has a direct impact on whether your training run succeeds or crashes with an out-of-memory error. The problem: full fine-tuning is expensive. Full fine-tuning means updating every single weight in the model during training. For a 7 billion parameter model, that's 7,000 numbers that need to be stored, differentiated, and updated on every training step. The model weights alone consume roughly 14 gigabytes in FP16. But training isn't just the weights. You also need memory for gradients, optimizer states, and activations. Add those up and you're looking at 42 to 56 gigabytes total. That's the territory of an NVIDIA A100 with 80 gigabytes of VRAM, a card that costs around $30,000 if you can even find one in stock. Scale up to Llama 3.170B and the numbers become almost comical. 280 to 400 GB of training memory requiring multiple H100s running in parallel. That's infrastructure that only large companies can afford. For the rest of us, full fine-tuning is simply not on the table. Training times are long, electricity costs are real, and the hardware doesn't exist in most budgets. That's exactly why LoRa and QLoRA were invented, and why they become the standard approach for everyone outside a hyperscaler. The solution: LoRa low-rank adaptation. Here's the core insight behind LoRa. Instead of updating all the weights in the model, you freeze them completely and inject small trainable adapter matrices alongside them. The original model never changes. You're training the adapters, and only the adapters. As the LoRa paper puts it, you're fine-tuning low-rank matrices instead of the actual model weights. That one idea is what makes fine-tuning accessible on consumer hardware. Python W equal torch re-aining 1 standard parameters. This is the weight matrix you'd normally fine-tune. A 1 standard by 1 standard matrix, 1 million parameters. In a real transformer, you'd have dozens of matrices like this, each much larger. The point isn't the specific size, it's that updating W directly means storing gradients and optimizer states for every one of those million values. That's what makes full fine-tuning so expensive. Python A equals torch range 108 hashtag 8000 parameters B. A equals torch range 108,000 parameters 8,000 parameters. Total trainable 16,000 instead of 1,000. Matrix A is 1000 by 8 and matrix B is 8 by 1000. Each has 8,000 parameters, 16,000 total. Compare that to 1 million. You've just reduced your trainable parameter count by 98.4% for this single layer. The number 8 here is the rank, and it's the central dial you'll turn to control the trade-off between capacity and memory. During training, W stays completely frozen. Only A and B receive gradient updates. The effective weight change is computed as delta W equals B multiplied by A minus A matrix of exactly the same shape as W but produced from two tiny factors. At inference time, you can either merge the result directly into W to get a single updated weight matrix, or keep the adapters separate and add their contribution on the fly. Both approaches give identical results. Full fine-tuning. W pre-trained, W updated, LoRa W pre-trained, W frozen plus A cux B. The diagram makes the contrast concrete. In full fine-tuning, every arrow in the network gets updated. The entire weight tensor flows backward through the optimizer. With LoRa, W is locked in place. The only thing that trains is the small A times B product sitting alongside it. Same forward pass, dramatically smaller backward pass. That's where the memory savings come from. The frozen weight matrix W on the left represents the full pre-trained model, billions of parameters that you never touch. LoRa A has dimensions R by D, and LoRa B has dimensions D by R, where R is the rank you choose. Their product, A times B, has the exact same shape as W, so you can add them together cleanly. The result, W plus AB, is your adapted model. Notice that the rank R controls the bottleneck width. Smaller R means fewer trainable parameters. Larger R means more expressive adapters. The entire pre-trained model's knowledge stays intact. You're layering new behavior on top of it. The numbers here are what make LoRa genuinely exciting. Full fine-tuning of Llama 3.8b requires updating all 8 billion parameters and consumes roughly 48 gigabytes of VRAM. With LoRa at rank 16, your trainable parameter count drops to somewhere between 8 and 16 million, that's 0.1 to 0.2% of the total, and training memory falls to 14 to 20 gigabytes. A 95% memory reduction achieved by training less than 1/4% of the model. That's not a compromise, that's an engineering win. The rank R is the most important LoRa hyperparameter you'll tune. It controls how many dimensions the adapter matrices operate in. Common values are 8, 16, 32, and 64. Higher rank means the adapters can represent more complex transformations, but it also means more trainable parameters and more memory. For most fine-tuning tasks, R equals 16 is the right starting point. Python #R8, fewer parameters, fastest training, lowest memory risk may underfit on complex tasks, #R16, balanced, good default for most projects. Best starting point before tuning further, #32, more capacity, slower, higher memory hashtag, used when R equals 16 underfits #R equals 64, high capacity for complex tasks, significant resource cost, use with care. Think of rank like the width of a bottleneck channel. A narrow channel is fast and cheap, but limits how much information can flow through. A wide channel is more expressive, but costs proportionally more. The research consensus is that R equals 16 hits the sweet spot for most instruction following and domain adaptation tasks. Start there, evaluate your results, and only increase if you see clear signs of underfitting. The alpha parameter is a scaling factor that controls how strongly the LoRa update influences the base model's output. The most common convention is to set alpha equal to R, so if your rank is 16, set alpha to 16 as well. This keeps the effective scale of the adapter contribution stable as you change R. If you want the adapters to have more influence, increase alpha relative to R. If the model is drifting too far from its original behavior, lower it. Target modules determine which layers in the transformer actually receive LoRa adapters. The most common choice is the attention projections. Q project, K project, V project, and O project, which covers the query, key, value, and output matrices in every attention head. For more expressive fine-tuning, you can extend that to the feed-forward network layers as well. Gate proct, up proct, and down proct. More target modules means more trainable parameters and more memory, but also more capacity to reshape the model's behavior. Attention only is the right default for most tasks. LoRa dropout applies dropout regulation to the adapter outputs during training. A value of 0 is common when your dataset is large enough that overfitting isn't a concern, and it's the default in on sloth. A value of 0.05 adds a small regularization effect that can help on smaller datasets. Avoid going much higher than that. Heavy dropout in LoRa adapters tends to slow convergence without proportional quality gains. Python model, fast language model, .get paved model, R16, LoRa Alma for 16, LoRa DOPS 0, target modules QProgs, KProgs, VProgs, OProgs, bias none, rank 16, alpha 16, no dropout, attention layers only, and bias set to none, so we're not wasting parameters on bias terms. When you run print trainable parameters, the output you're looking for is that trainable percentage, right around 0.13%. That number confirms LoRa is configured correctly. You're training roughly 10 million parameters out of 8 billion. Everything else is frozen. QLoRA, LoRa plus quantization. QLoRA takes everything you just learned about LoRa and adds one more layer of efficiency. It quantizes the base model itself down to 4-bit precision before training begins. The adapters still train in higher precision, but the frozen weight matrix that makes up 99.9% of the model's memory footprint is compressed from 16 bits per value down to 4 point. That single change cuts the base model's memory by 4x. To understand why 4-bit quantization works, it helps to think about what bit precision actually means for a number stored in memory. FP16 16-bit, 65,536 possible values, high precision indeed, 8-bit, 256 possible values, moderate precision in 4-bit, 16 possible. Each weight can take one of 65,536 distinct values, enough precision to represent subtle numerical differences accurately. Drop to 8 bits and you have 256 possible values. At 4 bits, just 16. That sounds alarmingly coarse, but here's what the research consistently shows. Neural network weights are highly redundant, and the model's behavior is determined far more by the pattern of weights than by their exact values. Quantizing to 4 bits introduces a small amount of noise, but the LoRa adapters trained in full precision compensate for it. The practical result of 4-bit quantization is a 4x reduction in model size. A 7B model that occupies 14 GB in FP16 shrinks to roughly 3.5 GB in 4-bit. Training memory drops accordingly, from around 20 GB with standard LoRa to around 8 GB with QLoRA. The adapters themselves are still computed and updated in higher precision, so the learning signal remains clean. You get the memory footprint of a compressed model with a training stability of full precision adapters. Here's the comparison that makes the choice concrete. Full fine-tuning of a 7B model in FP16 requires roughly 48 GB of training memory. That's an A100 territory. Standard LoRa brings that down to around 20 GB, which fits on an RTX 4090 with 24 GB. QLoRA at 4-bit drops it further to around 8 GB, comfortably fitting on an RTX 4070 with 12 GB. Each step down the table roughly halves your memory requirement, and each one is achievable without meaningful quality loss. Here's the table that matters for your specific setup. 2 Tesla P40s with 24 GB each. A 7B model with full fine-tuning needs around 48 GB doesn't fit. With LoRa it needs around 20 GB fits. With QLoRA around 8 GB fits easily. A 13B model with LoRa needs around 35 GB, too large. With QLoRA around 15 GB fits. A 30B model with QLoRA comes in around 22 GB fits. A 70B model with QLoRA needs around 48 GB, too large for a single P40. The headline result: QLoRA unlocks 13B models on your 24 GB GPU. That's a meaningful capability upgrade over standard LoRa. Python #load-based model with 4-bit quantization QLoRA model. Tokenizer equal fast language model from pre-trained model name unsloth Llama 3 8B BMB 4-bit, max a seek length of 2048, load in 4-bit Durkheim, hashtag this activates QLoRA, load in 4-bit Duko, printf model memory footprint, model get memory footprint splash 1E9 20 FGB, hashtag expected 5 8 GB. The critical line here is load in 4-bit Duko. That single flag tells Unsloth to load the base model weights in NF4 format. Everything else in the setup is identical to standard LoRa. The model footprint printout should land between 5 and 8 gigabytes. If you see a number significantly higher than that, double check that load in 4-bit is set on both the from pre-trained call and the get paved model call. The research on QLoRA quality is consistently reassuring. With a well-constructed dataset of 100 or more examples, QLoRA matches LoRa quality on nearly every benchmark. In some cases, it performs marginally better. The quantization noise acts as a form of regularization, preventing the adapters from overfitting to quirks in the training data. The scenarios where QLoRA can fall short are narrow, very small datasets under 100 examples, tasks that genuinely require high numerical precision, or models already under 1 billion parameters, where the base model is small enough that quantization noise is proportionally larger. For everything else, and that covers the vast majority of practical fine-tuning projects, start with QLoRA. Switch to LoRa only if you measure a quality gap. VRAM calculations for your Tesla P40. Python def model memory guess p params be bits overhead equal 1.2. Params be model size in billions of parameters bits precision 64 for 4-bit overhead CUDA context and MISC overhead factor bytes per parama equals 8 base की spore 16 byte win folk 16.8 QoC print F7B at 4-bit 4.1F GB hashtag prim is 7.8 GB. This function gives you a fast back-of-the-envelope calculation before you commit to loading a model. The formula is straightforward. Multiply parameter count by bytes per parameter, then apply a 1.2x overhead factor for the CUDA context and miscellaneous allocations. The output tells you the model's static memory footprint, what it costs just to hold the weights in VRAM, before any training overhead is added. A reliable rule of thumb: training memory runs 2 to 3 times the model's static memory footprint. That multiplier accounts for gradients on the trainable parameters, optimizer states, and the activation tensors that accumulate during the forward pass. For QLoRA, the multiplier is closer to 2 because so few parameters are trainable. The gradient and optimizer overhead is small relative to the frozen quantized weights. Python def training memory tissue b params b bits batch size 1 seek length 2048 base equal model memory tissue b params b bits hashtag trainable fraction 0.2% for LoRa trainable frac equals 0.001 if bits equals 4, else 0.002 grad optimizers equals params best p sclay 1a9 trainable frac 43 sclay 1a9 activations equals best size seeklen 4962 para 1a9 return base plus configs equals 7b LoRa 716 7b QLoRA 74 13b LoRa 1316 13b QLoRA 134 for name params bits fits equals fits if its if memeliga GPU VRAM else fits too large printf name for GB minus fits. The check marks and crosses in the output are your quick reference guide. Watch for the 13b LoRa line. It'll show roughly 35 gigabytes with a cross, confirming it won't fit on a single P40. The 13b QLoRa line shows around 15 gigabytes with a check mark. That's the practical value of this function. Run it before you start training, not after you hit an out-of-memory error at 2 a.m. The results confirm what the theory predicts. 7B with LoRa needs around 20 GBs, fits on your P40s. 7B with QLoRa needs around 8 GBs, fits with headroom to spare. 13B with LoRa needs around 35 GB, exceeds the 24 GB limit. 13B with QLoRa needs around 15 GB, fits comfortably. These numbers should guide your model selection before you write a single line of training code. When you do hit an out-of-memory error, there's a clear hierarchy of fixes to try. First, switch from LoRa to QLoRa. That alone gives you a 4x reduction in base model memory. If you're already on QLoRa, reduce per device train batch size to 1 and compensate with gradient accumulation steps equals 4 to maintain an effective batch size of 4. Reduce max EQ length from 2048 to 1044 if your data allows it. Lower the LoRa ramp. Finally, enable gradient checkpointing. It trades roughly 20% of training speed for a significant reduction in activation memory. Work through these in order and you'll almost always find a configuration that fits. Python training argues, training arguments, per device train batch size 1. Gradient accumulation steps 4. Hashtag effective batch size 4 gradient checkpointing to I. Hashtag memory to speed to. A batch size of 1 with 4 accumulation steps gives you the gradient quality of a batch size of 4 without storing 4 batches of activations simultaneously. Gradient checkpointing recomputes activations during the backward pass instead of storing them. The memory saving is real. The speed cost is modest. The 8-bit Atom optimizer is worth calling out specifically. Standard Atom stores 2 floating point optimizer states per parameter, which on 10 million trainable parameters adds up. The 8-bit version cuts that overhead roughly in half. LoRa versus QLoRa. Decision guide. Reach for standard LoRa when your model fits comfortably within your VRAM budget and you want the fastest possible training speed. It's also the right call for models under 1 billion parameters, where quantization noise is proportionally larger, and for tasks with genuine numerical precision requirements. If you've already tried QLoRa and measured a quality gap on your specific dataset, LoRa is the obvious fallback. QLoRA is the right default for the majority of fine-tuning work. Choose it when VRAM is your binding constraint, when you're working with 7B or larger models on consumer or prosumer hardware, or when you want room to experiment with higher ranks or additional target modules without blowing your memory budget. With a dataset of 100 or more quality examples, QLoRa will match LoRa in output quality while consuming roughly half the VRAM. For 7B models on your P40, either approach works, but QLoRa gives you more headroom for experimentation. For 13B models, QLoRa isn't just preferred, it's the only option that fits. And for your first fine-tuning project, starting with QLoRa is the pragmatic choice. It leaves you buffer for debugging, larger batch sizes, and longer sequences, all of which matter more than the marginal quality difference between the two methods. Practical example. See the difference. Python hashtag LoRa FP16 base model LoRa underscore fast language model from pre-trained unsloth llama 38b load in 4-bit fulls. LoRa mem equal model LoRa get memory footprint here 1A9 print F LoRa memory footprint here 1A GB hashtag umoj 1820 GB hashtag QLoRa 4-bit base model underscore LoRa ISCO call fast language models from pre-downproxed load in 4-bit to count. QLoRa mem equal model QLoRa get memory footprint QLoRa mem C footprint EKB Sharchagez 6 dense 8 GB savings Kul 1 bis QLoRA mem li LoRA mem plus QLoRA print if memory saved with QLoRA save. The LoRA model should land around 18 to 20 GBits. The QLoRA model should come in at 6 to 8 GBits. The savings line at the bottom typically shows 60 to 70%. What's worth noticing is that the QLoRA version is actually configured with more target modules. It includes the feed-forward layers in addition to attention, and it still uses dramatically less memory. That's the power of 4-bit quantization on the base model. Check your understanding. Here are 5 questions worth working through before moving on. First, what is the core idea behind LoRA? The answer is that instead of training all model parameters, LoRA trains small adapter matrices A and B that are added to the frozen original weights, reducing trainable parameters from billions to millions, a 99+% reduction. Second, if a 7B model has 7 billion parameters, how many are trainable with LoRA at R16? Approximately 8 to 16 million, which is 0.1 to 0.2% of the total. Third, what is the difference between LoRA and QLoRA? LoRA keeps the base model in 16-bit and trains adapters. QLoRA quantizes the base model to 4-bit first, then trains adapters in higher precision, using 4x less memory with minimal quality loss. Fourth, can you train a 13B model with regular LoRA on your Tesla P40? No, it needs around 35 gigabytes. But QLoRA brings that down to roughly 15 gigabytes, which fits. Fifth, what happens when you increase rank from R equals 16 to R equals 64? You get 4 times more trainable parameters, more expressive adapters, higher memory usage, slower training, and increased overfitting risk on small datasets. Assignment: calculate your project's memory. Before the next lesson, work through this calculation for the model you plan to fine-tune. Pick your target model size: Tiny Llama at 1B, Llama 3 8B at 7B, Llama 3 13B or larger. Run the training memory DSP function from this lesson for both LoRA and QLoRA configurations. Verify that at least one of them fits within your 24GB DSP40 budget. Then decide which method you'll use and write down your reasoning. The example below shows what a completed analysis looks like. Model 7B parameters LoRA memory estimate 20 GB fits 24 GB P40. QLoRA memory estimate model 8 GB fits with headroom decision. QLoRA reasons minus 16 GB of headroom for larger batch sizes and longer sequences. Room to increase rank to R equals 32 without hitting the bind. Memory ceiling enables experimentation with feed-forward target modules, matches LoRA quality with 100+ training examples. The decision here isn't just both fit, pick one. Notice the reasoning. 16 GB of headroom means you can increase rank, add target modules, or use longer sequences without rerunning memory calculations every time you change a hyperparameter. That flexibility is worth more than the marginal speed advantage of LoRA during the experimentation phase of a project. Key takeaways. Here's what to carry forward from this lesson. Full fine-tuning is impractical for individuals. A 7B model alone needs 48 gigabits of training memory and hardware most people can't access. LoRA solves this by training small adapter matrices instead of the full model, cutting trainable parameters by 99+% and training memory from 48 GB down to around 20 GB. QLoRA goes further by quantizing the base model to 4-bit, dropping training memory to around 8 GB with minimal quality loss. For your Tesla P40 with 24 GB 7B models, work with either method. 13B models require QLoRA and 30B models fit with QLoRA. The 3 LoRa hyperparameters that matter most are rank R, where 16 is the balanced default, alpha, which you typically set equal to R, and target modules, where attention only is the right starting point. Quality is preserved with both methods when your training data is solid. Next lesson. Now that you understand how to make fine-tuning fit on real hardware, the next question is which model to actually fine-tune. Lesson 1.5 covers model types and selection, how to evaluate your options, what the architecture differences mean for your use case, and how to pick the right starting point for your specific project. If you want to go deeper on the theory covered here, the original LoRA paper is LoRA, low-rank adaptation of large language models, and the QLoRA paper is QLoRA, efficient fine-tuning of quantized LLMs. Both are worth reading. The Ansloth documentation at github.com/AnslothAI Ansloth covers the practical API in detail. Skip. This chart compares GPU memory requirements across full fine-tuning, LoRA in BF16 and QLoRA in 4-bit for several model sizes. The pattern is consistent and stark. Full fine-tuning bars dwarf the others at every model size. For a 3B model like Llama 3.2, full fine-tuning already consumes a substantial fraction of a high-end GPU's memory. LoRA and QLoRA compress that requirement dramatically, enough that QLoRA on a 3B model fits comfortably on a 12 GB RTX 3060. The key insight from this chart isn't the specific numbers, it's that the memory gap between full fine-tuning and parameter-efficient methods grows with model size. The larger the model you want to work with, the more essential LoRA and QLoRA become. This table maps quantization levels to their memory cost and relative training speed. FP32 at 32 bits costs 4 gigabits per billion parameters and trains at 0.1x relative speed. It's the baseline for numerical precision but completely impractical for large models. FP16 and BF16 at 16 bits cut that to 2 GB per billion and run at roughly 1x speed, the standard for LoRA training. INT8 at 8 bits drops to 1 GB per billion and doubles training throughput. INT4, the format QLoRA uses, costs just 0.5 GB per billion parameters and runs at around 3x the speed of FP32. The extreme end, GGUF-Q2 Kulske at 2 to 3 bits, reaches 4x speed at 0.3 culs per billion, though at meaningful quality cost. For fine-tuning, INT4 via QLoRA is the practical optimum. It sits at the point where memory savings are largest and quality loss is still negligible. This bar chart shows the fraction of total parameters that are actually trained under LoRA versus full fine-tuning, broken out by model size. The full fine-tuning bars sit near 100% across the board. By definition, every parameter is updated. The LoRA bars tell a different story. 0.4% for a 3B model, dropping to 0.3% for 7B, 0.25% for 13B, and 0.5% for 70B. Notice the trend. As models get larger, LoRa's trainable fraction gets smaller. That's because the adapter dimensions are determined by rank and target module count, which don't scale with model size the way the base weight matrices do. The practical implication: LoRa becomes proportionally more efficient as models grow. On a 70B model, you're updating roughly one parameter in every 650. That's why LoRa is the enabling technology for fine-tuning at scale. This chart plots VRAM requirements against model size for full fine-tuning in FP16, LoRa in BF16, and QLoRA in 4-bit. The horizontal axis runs from 1 billion to 70 billion parameters. The vertical axis shows VRAM in gigabytes. The full fine-tuning bars grow steeply. At 70B, they extend far beyond what any single consumer or prosumer GPU can provide. The LoRa and QLoRA bars remain substantially lower across every model size, with QLoRA consistently the most compact. The two horizontal reference lines you want to keep in mind for your setup are 24 GB for a single Tesla P40 and 48 GB for both P40s combined if you configure multi-GPU training. Reading the chart against those lines immediately tells you which model sizes are accessible to you under each method. This chart compares output quality and training time for full fine-tuning LoRa and QLoRA at different ranks. Full fine-tuning scores 100% quality and takes 100% of the training time. It's the baseline. LoRa at rank 16 achieves 96% quality in just 35% of the training time. At rank 64, it reaches 98% quality in 42% of the time. QLoRA at rank 16 scores 93% quality in 20% of the training time, and at rank 64, 95% quality in 25% of the time. The trade-off is clear. You give up 2 to 7 percentage points of quality and gain 58 to 80% of your training time back. For most practical applications, that's an excellent exchange. The quality numbers also confirm that increasing rank from 16 to 64 recovers roughly half the gap between QLoRA and full fine-tuning. Useful to know when you're deciding whether a higher rank is worth the extra memory cost.